Everybody's Tyler here at Chesney Champs, checking in with team number 3476. Code Orange, by the way, I'm here with Jolyn, Coneth, and Varun. And Code Orange, absolutely phenomenal. 2 regional wins this year. Finalists at championships as well, too, showing off the great prowess that Code Orange has been doing for many, many years. Of course, we're going to follow the cargo journey through the robot, but you're going to hear about some cool programming features and some other awesome functions coming up here on Behind the Bumpers.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. SOLIDWORKS is free for first teams. Over 80% of U.S. engineering schools and 370,000 plus companies use SOLIDWORKS to design great products. SOLIDWORKS can help you design a great robot on desktop or on the cloud. Go to solidworks.com/first to register your team. First alumni and mentors are making Stryker a top priority for their internships and careers. That's because Stryker knows that those in First are the leaders and innovators of tomorrow. If you want to help make the world a better place by creating life-saving medical devices and technology, get started at careers.stryker.com.
So let's start out with your intake and follow that ball journey through. We're going to be kind of talking about some different automation processes and sensors as well. So love to hear about the mechanical aspect. How did you end up with this? And of course, any sensors that went into it as well.
Yeah, definitely. So when we were designing our intake, we were primarily considering ways to minimize damage to it, and then if damage did occur, how we could swap it out pretty easily. So the first thing I want to point out is how we have implemented our pneumatics right here. And as you can see right now, the intake is out, so the pneumatics are retracted. This is actually opposite of the design we had last year, because we noticed that when it was out while this intake was in, the pneumatics would break a lot easier. So now we have it the other way. Another thing I want to point out is our intake is retained by 6 pins, so there are 3 right here, and similarly on the other side. This makes it really easy to swap out for a spare intake if we ever do run out of time in between matches.
And you guys have some ejection automation that you're doing too, so talk to me about color sensing, and then if we can show a demo of this working too, it'd be great.
Yeah, so as you can see, we have this programmed to intake the blue colored ball right now, and that is why the red color is being ejected by this, which we implemented between regionals since we wanted to make cycles more efficient for our drivers. Another mechanical feature that we have on both our intake and our eject system are these mechanism wheels right here. These ones are custom 3D printed, but we implemented them because we wanted to be able to intake cargo from the sides. These plates also function similarly to funnel them into our ball path and into the hopper. And then one more iteration I would like to point out on the intake is over here near the motor. So right here we have this belt and pulley going here. We added this bearing right here because we used to have a problem where this belt would flip over, and we would have to adjust that a lot. So we added this as a way to retain it.
Let's keep moving on through your robot and hop next into your hopper area, and Conant's going to talk more about that, and we'll talk about, of course, the construction of it and any sensor that's gone into it as well.
So the first thing I'd like to point out is our flow overall. So we have a polycord system that starts here, and it's strung by these polycord belts, and it's driven by this one motor right here. So we have one motor driving the entire polycord system. It drives this belt, which is driving these polycord belts, and we have these stars that push the ball right when we're up by the feeder wheel.
Sure.
This helps so that we don't get balls stuck there, and it helps so that we push our balls out and don't leave them just sitting in the robot, right?
How'd you come up with the star design? Like, were you trying something else first and then you came up with that, or what was the process behind that?
I believe we originally tried it with these 2-inch wheels.
Sure.
But it didn't work out well, so we decided. So then we cut these wheels, the round part off, and we just used it spoked, and we ran with that for a while. And then we realized we could just 3D print our own out of a stronger material. So this is Ninja Flex. It's a flexible 3D printed material, and it pushes the ball out and it works perfectly. From there on, we also have a belt that runs over here that drives the belts, or these polycord belts, from here and in the middle down there, pushing the ball all the way up to the top of the robot, right next to the feeder wheel. On the back, we have this strip of tape. This is so that we have a little more grip onto the backing, this polycard backing, and it works pretty well. We haven't had any issues. Occasionally we have to retape it, but it works pretty well, and it's a pretty simple fix.
And also, I'd like to point out, can you hold this? We have a beam brake sensor like right over here So what it does is that if it breaks, it will turn on the hopper so that we can, because our hopper is big enough that we can hold 3 balls in it. So we wanted to avoid the possibility of getting that penalty for 3 balls. So what we do is if we detect a 3rd ball in for like a little over 2 seconds, we automatically hood eject 1 ball so that we don't get that penalty for holding 3 cargo. So if you just, if you can intake 3 cargo into the ball, we can see it. We can see how it would work. We actually have it currently disabled right now because at Chesney we're a little bit more relaxed on those rules, so we didn't want to put that. But we can see that when the ball gets broken by that beam break, it gets automatically pushed up. And so it would be automatically running it. Normally we would automatically hood eject like that, and then it would just stop.
So from here, I'm going to go to the shooter. This is a pretty similar design to our previous 2020 robot. It uses the hood, and we have our 3D printed rack right here connected to our Neo pinion. This worked for us really well in the 2020 season. We originally started with a full 3D printed rack, but from there we needed to reduce weight, so we moved to 2 smaller ones. That's connected to these 2 smaller 3D printed pinions, which are connected to our Neo motor, and this works pretty well. We can show you the hood in action.
So I'd like to point out that compared to last year, we made our teeth much larger because at Beach Blitz last year during when we were in our elims, we had the teeth wear out, and that's what lost us the match because we couldn't shoot anymore. So we made them much larger. We've been using these since the beginning of season, since our first regional, and they still look pretty much new. So on the programming side of things for our hood, you notice that we'll have a limelight here, and so we don't actually use any limelight data directly. So we do pose estimation from our limelight, and we put that into our robot tracker, and we use our robot tracker to shoot. So what's really cool here, if you can come over here, so we have a table basically based on distance away from the goal, and then we have flywheel speed and hood ejection angle. So based on the distance away from the goal, we can automatically shoot, and we can shoot from anywhere in the goal. We were able to get this working really early in the season. At our first regional, we had this system up and running, and that's what caused us to win because we just shot the best. In addition to that shooter stuff, we also have our auto system here. So if you watched Behind the Bumpers last year, you'll recognize this, but it's been upgraded a little bit. We now use reflection for setting the shooter, for running scripts on the robot, and it's now completely open source and ready for any other team to use. So if you guys want to try this out, you can just search up Auto Builder on our GitHub, and you'll find there's documentation for you to use it if you want to.
Brian, I want to ask you, there was an update that came out recently. You said that First is looking at using April tags now for this year as well, too. Does that excite you that they're looking at implementing that?
Yeah, so April tags is something I've always wanted to implement something where we have global pose estimation everywhere, so that we can potentially do more autonomous stuff while we're driving, and having the access to the more accurate pose estimation just opens up so many possibilities for the amount of automation you can do.
Yeah, looking forward to it. Let's keep moving on. We'll talk about your climber on your robot. So I think we'll start on the mechanical side a little bit, and then we'll go ahead and talk more about any programming and automation that's gone to your climber as well.
So this is our 2022 climber. It is driven by 2 Falcon motors, and our primary source of going up is our elevator. We can show you the climb sequence in action. And we have our friction brake to stop us from going down once we've grabbed onto the bar. And this is our climb sequence. We have to do our pivot. Force advance. Force advance.
So that probably looked really complicated, and it is kind of complicated. So what we've done is we've completely automated the climb. So basically all the driver does is they press one button on our control panel over here, and the robot will automatically climb. So you'll notice how at certain points it stopped, and I have to press another button. And that's because our robot uses our climb sequence checks the gyro angles, and it was checking for if we're on the correct part of the swing. And since we're on flat ground, we're not on the correct part of the swing. So That's why we had to manually force advance it. But during climb, what this basically allows us to do is we press one button and our robot automatically climbs for us. We don't have to worry about it. We have contact switches over here and over there that tell us when these latches are closed, because this is probably one of the most critical parts of our climb. We can demonstrate to you how these, Connor can demonstrate to you how these are like an over-center design and prevent us from falling over.
So this is these are our climber hooks. They work through an over-the-center design. From here, we're able to use our pneumatic piston and push up or extend the piston, making the hook open. And once we reach a certain point, we are able to close these pistons. As you can see, because of this over-the-center design, we're able to lock our robot onto the bar very strongly. In fact, these plates will break before we actually come off of the bar. And that's because of the over-the-center design. So, yeah, right now the pneumatic isn't engaged, but if you try, you can't pull that off. But if you just push right here, it's really easy.
What made you come up with this type of design? What was the impetus behind it?
So, in our, I believe, 2016 robot, we had a similar design that we used for the four-position hood.
Sure.
And we kind of copied that design. We realized that it worked really well, and it was a really good use. It was a really good option that we had for this type of problem, and it's worked out really well since.
Let's try to wrap up on your robot here. Let's talk about some electronics. You guys have done a great job with the wiring of it. I know you got some on the underbelly as well too, so we'll get the robot kind of back in the shape it needs to be, and wrap up talking more about your electronics.
All right, so lastly, we're going to talk about our electronics, because the way we designed this, we thought a lot about in the initial stage. So right here, we have most of our components on the underside of the belly pan, and this was done intentionally because we tried this out first in 2020, and it worked out well for us because we had a lot more space on the top of the drive base, and we could access a lot of this wiring more easily and debug that as well. So another thing we considered while doing this was in 2020, the game pieces were able to compress a lot more, and sometimes they got stuck underneath the drive base, and that was one of our concerns during that year. But this year, we noted that the game pieces were much larger, so they would not be able to get caught underneath.
Well, I think with those standoffs too, having the bump in the middle of the field too, it probably helps you out a lot with that, especially with your short drive too.
Yeah, it definitely does.
Well, Code Orange, thank you so much for taking the time to tell us about your robot here. Congratulations on a fantastic season, by the way, and can't wait to see, of course, how you do here at Chelsea Champs, and then can't wait for future robots too. Thanks a lot for taking the time.
Thank you.
This video on First Updates Now is made possible by viewers like you and also the following sponsors. First alumni and mentors are making Stryker a top priority for their internships and careers. That's because Stryker knows that those in First are the leaders and innovators of tomorrow. If you want to help make the world a better place by creating life-saving medical devices and technology, get started at careers.stryker.com. SolidWorks is free for first teams. Over 80% of U.S. engineering schools and 370,000 plus companies use SolidWorks to design great products. SolidWorks can help you design a great robot on desktop or on the cloud. Go to solidworks.com/first to register your team. Don't forget to like, subscribe, and ring the bell to stay up to date on our new videos. Keep the conversation going and provide your input to our content. Watch our live shows at twitch.tv/firstupdatesnow. Join our Discord at discord.gg/firstupdatesnow, and check out Fun FTC on Facebook, Instagram, and Twitter, and First Updates Now on Facebook, Instagram, TikTok, and Twitter.